Launched on Christmas Day 2021, the Webb telescope is the bigger, cooler sibling of the Hubble Space Telescope, equipped with super-powerful infrared instruments that make it a perfect time machine.
Well, it turns out it's so powerful it might have just shattered our understanding of the universe.
By peering into the past, James Webb allows us to detect incredibly old and faint objects, such as distant galaxies and celestial bodies from the early universe. However, the images captured by James Webb are causing quite a stir among astronomers and cosmologists, as they challenge the very foundation of our understanding of the universe. Thus, in the 2 years since James Webb launched, renowned American physicist Michio Kaku and other scientists have learned one thing: the early universe is a lot weirder than we thought.
That shouldn't happen. There should not be primordial galaxies that are bigger than the Milky Way galaxy that are only 500 million years old. Something is wrong. We may have to revise our theory of the creation of the universe.
Join us as we dig deep into how James Webb just proved us wrong. When Einstein first put forth his new theory of relativity, it forever changed how we think of space and time. Space isn't fixed like a three-dimensional grid with universally agreed upon distances between any 2 points. Nor is time a continuously flowing entity where you can sync up your clocks, move anywhere you like, and be confident that your clock reads the same as anyone else's. Instead, we experience space and time as relative. Your motion through space affects your motion through time, and vice versa. This was the core idea behind special relativity, which led us to discard our older ideas of absolute space and absolute time, instead replacing them with the notion of space-time. As you move through space relative to another observer, your clocks appear to run differently according to Einstein's laws. Special relativity works perfectly for all observers, whether they're at rest or in motion, and represented an enormous leap in understanding our universe over Newton's original laws of motion. But this idea, brilliant though it was, didn't include gravity. The old Newtonian picture of gravity was inherently tied to absolute notions of distances and times and was incompatible with the notion of space-time. It took over a decade for Einstein to bring gravity into the fold, taking us from special relativity to general relativity, incorporating matter and energy into the equation. Instead of the flat space-time of special relativity, the presence of matter and energy allowed for space and time to be dynamic entities. No longer bound to be static, the universe could expand or contract depending on what was in it. Matter and energy told space-time how to curve, and that curved space-time dictated how matter and energy would move. This relationship, first put forth more than 100 years ago, has been tested by an enormous suite of experiments and observations, with Einstein's theory passing each and every one. General relativity applies not only to the gravity we find on Earth and elsewhere in the solar system, but on vast cosmic scales that dwarf our own. Galaxies, clusters of galaxies, and even to the entire universe itself. This last part is particularly fascinating. If we take a universe that's uniformly filled with matter and energy, including a combination of different forms of matter and energy, that universe must either expand or contract. It cannot remain in a static state for more than an instant, even if it starts off in one. In 1922, Alexander Friedmann demonstrated this, deriving from Einstein's theory, the Friedmann equations, the equations that govern the expansion of the universe. The very next year, Edwin Hubble measured the distance to Andromeda, determining that this spiral nebula was in fact its own galaxy far beyond and outside the Milky Way. Subsequently, we measured distances to large numbers of galaxies, while also independently obtaining measurements of the light coming from them. What we found, almost universally, was the following. First, the farther away a galaxy was, the redder its light was. Second, that this was true even though the stars inside the more distant galaxies were, on average, intrinsically bluer than the stars we see in nearby galaxies. Third, the explanation for this was consistent with the idea that light emitted by galaxies with the same frequencies and wavelengths that light is emitted by here in our own galaxy was being redshifted by the expansion of the universe. Alternative explanations, such as tired light, disagreed with the observations, leaving only those explanations that included the expanding universe as viable. When taken all together, there was no escaping that conclusion. The universe itself was expanding, and that expansion was responsible for the observed redshift of light that originated from far away. To be fair, the expanding universe theory has the advantage of internal consistency. A theory's rational, mathematical beauty is beguiling to scientists. Fair enough, but for a theory to be a useful paradigm for describing reality, it must also display external consistency. Its assumptions and predictions must match observable phenomena. This is where the expanding universe theory falls short. It is not consistent with all that is the case in the universe. Anomalous data from James Webb are increasingly pressing against the dominant paradigm of astrophysics. James Webb, as you know, is the largest space telescope ever launched, is able to see back in time like never before thanks to a combination of its large mirrors and its sensitivity to infrared light. This means that it can see in stunning clarity objects whose light was emitted billions of years ago in the ultraviolet or visible portion of the spectrum, and has now been stretched by the universe's expansion to longer wavelengths than optical telescopes like Hubble. Astronomers are using it to peer back to near cosmic dawn, a time when the first stars and galaxies were forming. And the telescope is showing that these early galaxies are different than astronomers had anticipated, in a plethora of ways. Some are settling into shapes we didn't think were possible so eerily after the Big Bang. Others are unexpectedly large. As a result, over the past year, the press has been filled with news about phenomena that do not conform to the dominant paradigm. Very old galaxies that should not exist. In fact, exist. Galaxies nearly as massive as the Milky Way and full of mature red stars seem to be dispersed in deep field images obtained by James Webb during its observation campaign, and they are giving astronomers a headache. These galaxies, described in a study based on Webb's data release, are so far away that they appear only as tiny reddish dots to the powerful telescope. By analyzing the light emitted by these galaxies, astronomers established that they were viewing them in our universe's infancy just a few 100 million years after the Big Bang. Such early galaxies are not in themselves surprising. Astronomers expected that first star clusters sprung up shortly after the universe moved out of the so-called Dark Ages, the first 400 million years of its existence when only a thick fog of hydrogen atoms permeated space. But the galaxies found in the Webb images appeared shockingly big, and the stars in them too old. The new findings are in conflict with existing ideas of how the universe looked and evolved in its early years, and don't match earlier observations made by Webb's less powerful predecessor, the Hubble Space Telescope. As one of the authors of the study wrote, previous studies of the early universe with Hubble and other instruments tend to find small, blue baby galaxies at early times, objects which have just recently formed out of the primordial cosmic soup and are themselves building their early stars and structures. Young stars in general shine bright blue. With age, stars develop a redder glow as they burn through their fuel and cool down. In ancient galaxies that Webb was built to spot, astronomers had not expected to see old red stars. They also had not expected to find galaxies more massive than perhaps 1 billion suns. But those reddish dots revealed in Webb's deep fields appear 50 times more massive than that. This was astounding. We're finding galaxy candidates as massive as our own galaxy, when the universe was 3% of its current age. According to scientists, this is yet another big clue that the dominant paradigm about the universe expanding from a Big Bang is incorrect. The observations in the study mentioned is just one trickle in an increasing flow of data showing this. Astrophysics has many complexities, but one prediction of the expanding universe theory can be easily checked by observation, and thus the theory can be easily supported or defeated. The cosmologists tell us the universe is expanding. However, if the universe had been expanding for 12+ billion years, then we would see certain easily noticeable evidence. The expanding universe theory predicts that as space expands, the matter within space becomes less densely distributed, and galaxies become farther and farther apart. Introductory astronomy courses use a leavening ball of dough with raisins in it, raisin bread, to explain the theory. The claim is that every raisin is moving farther away from every other raisin, simple enough to understand. Logically, that means that as the loaf continues to rise, over time, the raisins will be further and further away from every other raisin. Therefore, as time goes by, the density of raisins within the loaf will decrease as the loaf expands, because the raisins will be spread more thinly. We see this phenomenon in rising bread dough, but do we see this in galaxies? The expanding universe theory predicts that, as time goes by, the density of galaxies within the universe will decrease as the universe expands, moving galaxies further and further away from each other, spreading them more thinly across space. The universe is billions of years old. It's not as simple as watching bread dough rise, but we can indeed look at galaxy density across both space and time to support or defeat the expanding universe theory. A light year is both a measure of time and distance. If an object is 1 light year away from us, then light takes 1 year to reach us. That means that the light we see is as the object was a year ago. So when astronomers talk about galaxies billions of light years away, they also mean their observations are of those objects as they were and where they were billions of years ago. The expanding universe theory says that as space expands, over time galaxies spread out and get farther from each other and become less densely packed in space. The theory predicts that we would see a lower density of galaxies 2 billion light-years away than 8 billion light-years away. If the universe had been expanding all that time, then the galaxies 8 billion light-years away would, on average, be closer together than galaxies at a closer distance. It is simple to measure this, and measurements of galaxy distribution have been made. All surveys show that there is no significant change in the relative density of galaxy distribution across the universe, which means no difference over space or time. There is clumping in the universe where there are spots of greater matter density. However, the level of this clumping is the same at all distances. The density of galaxies in regions 8 billion light-years away is not different from the density of galaxies in regions 2 billion light-years away. Take any two distances, and the same is true. Thus, since distance in space equals distance in time, the observations confirm that the density of galaxies 8 billion years ago is not different from the density of galaxies 2 billion years ago. Therefore, we must conclude that the expansion theory is contradicted by the evidence. In other words, James Webb's unexpected findings have led some scientists to question the very fundamentals of the Big Bang theory and explore alternative explanations for the structure and evolution of the cosmos. Another profound question raised by James Webb's observations is the age of the stars within the distant galaxies. According to the Big Bang theory, the galaxies farthest away in the Webb images represent a cosmic snapshot from around 400 to 500 million years after the universe's birth. However, some of these galaxies appear to house stars that are over 1 billion years old. This presents a significant problem, as nothing should be older than the Big Bang itself. Furthermore, the abundance of galaxies, some as massive as the Milky Way, just a few 100 million years after the Big Bang, challenges the notion of a cosmic dark age as predicted by the theory. These discrepancies in age raise important questions about the origins and evolution of the universe. All of this begs the question, has James Webb disproven the Big Bang? Before answer this question, you should know that the Big Bang Theory's predictions have been reliably wrong for decades. It's wrong about the cosmic microwave background, its temperature and smoothness. Wrong about the scale of the largest structures in the universe. Wrong about the abundance of lithium and helium. Wrong about the size, age, and brightness of distant galaxies. But instead of abandoning the theory, cosmologists have modified it many times to fit what has already been observed and to smooth over previous contradictions as precisely as the emperor's new clothes. The classic standard model required two conceptual pieces. The first, as told, was the stage on which the drama of cosmology would play out, and it came in the form of Einstein's general theory of relativity. What we get from general relativity is a space-time that expands continuously, starting just after the Big Bang. Into that expanding space-time, the classic standard model then poured all the matter and energy described in another standard model, the one associated with particle physics. The central tenet of classic Big Bang cosmology was that the universe began as a super-hot, super-dense soup of fundamental particles. These particles were described in the standard model of particle physics and included things like quarks, electrons, photons, and other actors. Which particles you deal with depends on when you begin the story. As you go farther back in time, you run out of data from particle physics experiments to guide your descriptions. Using the standard model of particle physics, the classic version of the standard model of cosmology then follows the soup of particles and energy as the cosmos expands, cools, and thins out. The model made many predictions, but its first and most stunning validation came in 1964, when astronomers discovered the universe was filled with fossilized light left over from a few 100,000 years after the Big Bang. Cosmic microwave background radiation, or CMB, became one of cosmologists' most important resources in pushing the bounds of their understanding. In time, CMB introduced a number of problems or paradoxes to haunt the classic standard model. The most pressing of these was the smoothness of the background radiation. CMB looked the same no matter where astronomers directed their gaze. This implied conditions across widely separated regions of the early universe were identical. It was like looking at the weather to find every city on the planet had the exact same temperature. Either a miracle occurred in the early universe, or the cosmic microwave background's smoothness had a deeper explanation. Since physicists do not like miracles, they sought the deeper explanation. What they came up with in the 1980s was inflation. According to this new idea, very early in cosmic history, a tiny sliver of space-time underwent a brief period of tremendous expansion. That blown-up region of the cosmos became our visible universe. Inflation, driven by a hypothetical unknown quantum energy field, was so successful at accounting for CMB and the other paradoxes of the classic model that it became the base of the new, modern version of cosmology. As of today, all cosmology is inflationary cosmology. The revision did not end there. There were two other additions to the story. The first was the recognition that there was more matter out there than could be seen with telescopes. By tracking the motion of luminous matter, the stuff that emits light, astronomers had to admit that there seemed to be a whole lot more unseen or dark matter exerting a gravitational force. Whatever this dark matter was, it was not included in that standard model of particle physics. It was something new. While scientists could not directly see dark matter, confrontations between theory and observations told astronomers that whatever it was, this matter was not moving at relativistic speeds. It had to be slower-moving stuff. In other words, the dark matter was cold. Further observations showed that the dark stuff constituted the vast majority of cosmic matter. Somewhere around 85% of cosmic mass was dark. The second addition was another unseen player. Using distant supernovae, astronomers in the late 1990s discovered that the universe's expansion was accelerating. This meant the whole cosmos must be full of an invisible form of energy, and this energy was pushing space apart. This dark energy constituted a full 75% of the universe's total energy budget. Inflation, cold dark matter, and dark energy are key players in the modern version of cosmology's standard model. Sometimes called inflationary cosmology and sometimes labeled the LCDM model, this is the story every student must learn and master. What they also will learn is the remarkable concordance between the model and observations. On top of all the successes of the classic version of cosmology's standard model, the modern version matches key features of ultra-high-resolution maps of the CMB. It also explains features seen in the large-scale distribution of galaxies. Without doubt, the modern standard model of cosmology is a triumph of the scientific process. However, on the other hand, the Big Bang Theory is also kind of a kludge. The modern standard model seems to glue together a bunch of disparate parts without any overarching theoretical structure. Take inflation and dark energy. In both cases, we have a form of pervasive energy that pushes space apart. Inflation does it really fast and then dissipates. Dark energy does it much slower and does not dissipate. As far as we know, these forces have nothing to do with each other. Inflation was invented in the 1980s to solve a particular set of problems, especially CMB smoothness. Dark energy was added later on to solve another issue, cosmic acceleration. Likewise, dark energy and dark matter are in no way related, and they do not appear in the standard model of particle physics. The dark components were forced into the picture based on observations, but they don't fit into anything else we know. Add all this up, and there are reasons to wonder about the modern version of the standard model. It is impressive, and its accounts match up to lots of data with astonishing accuracy. But much of it also seems cobbled together out of necessity. It is not hard to imagine some future physicist laughing at the idea of dark matter or dark energy because some cleaner, simpler theory did away with them. So, is there such a theory out there waiting to be found? Is our standard model just a placeholder for something so different we won't even recognize the old ideas within the ideas yet to come? Only time will tell. Regardless, free and open debate is essential to obtaining scientific truth. It is long past time for cosmologists to throw off this self-censorship and say openly that the Big Bang and expansion theory may be entirely wrong. It is also way past time to stop ignoring the alternative, that the universe is evolving but not expanding, and that there was no hot, dense state of the cosmos nor an origin for the whole cosmos. Let's have that open debate begin in scientific publications and conferences and in the mass media. It looks like Eric Lerner have put on their life jackets on board the sinking cosmic ship Big Bang, but are not yet ready to enter the lifeboats. They should not hesitate further. A rescue ship, no Big Bang, is standing close by at the ready. Time to get on board and chart a new course for the science of the cosmos. As we delve deeper into the mysteries of the universe, we inevitably encounter the perplexing concept of time. We've learned lots of surprising and counterintuitive lessons from our investigations of time. Time is relative, not absolute. Time always marches forward, not backward, but we still lack an explanation for the arrow of time. Thermodynamically, the universe has an arrow of time, which flows in the same direction as increasing entropy. And when we investigate the universe on a fundamental level, it turns out that time may not be fundamental at all. But existence itself, it's very, very difficult to take that property away from time and to still wind up with a universe consistent with what we observe. However, it's worth noting that despite the popular trend to question the nature of time, its physical realness is not in doubt. Time is an integral part of the universe, and the boundary between events that have been observed or measured to have a definitive outcome and those whose outcome has not yet been decided is the best way we have to define precisely what we mean by the moment of now. As esteemed physicist Lee Smolin said, in the Copenhagen version of quantum mechanics, there is a quantum world and there is a classical world, and a boundary between them, when things become definite. When things that are indefinite in the quantum world become definite. And what they're trying to say is that is the fundamental thing that happens in nature. When things that are indefinite become definite. And that's what now is. The moment now, the present moment, that all these people say is missing from science and missing from physics. That is the transition from indefinite to definite. After all, time may or may not be fundamental, and our perceived arrow of time may or may not be related to the thermodynamic arrow of time. But the fact that we can measure, observe, and quantify, it should put any doubts of its non-existence to rest. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.